In today's video, we are going to see how to differentiate log and exponential functions. So we will be taking derivatives of functions that involve e. E is the base. More derivatives with e. Then we'll do some derivatives with bases other than e, some natural log derivatives, and some log derivatives. So you'll think of these as another category, like the trig derivatives you started to memorize, but now we've got our e derivatives and natural log derivatives. So the first one that we're going to learn and work on memorizing is that the derivative of e to the x is e to the x. This is my favorite derivative because the derivative is the same as the original function. So if I have example 1, find the derivative of each of the following. If y equals 5 times e to the x, then dy dx is 5 times e to the x. The derivative and the original function are the same. For part B, to differentiate there, the derivative, I would take the derivative of e to the x and the derivative of negative 4x. The derivative of e to the x, as we see in our rule, is e to the x. And then from previous lessons, the derivative of negative 4x is minus 4. And then for part C, we'll apply what we know, dy dx. Derivative of 7 times e to the x is 7e to the x. And then the derivative of cosine is negative sine of x. So far, so good. That rule, the derivative of e to the x is e to the x, works when the only thing that's in the exponent, when it's just x. So the derivative of e to just x is e to just x. Now, if we take this exponent and it gets changed at all, then we need to apply the chain rule. So that brings us to the next section. Chain rule version. So here we have our derivative we just worked with. But if the exponent is anything other than x, then we've got to use our chain rule. So here's how we do the chain rule. The derivative of e to the u is e to the u, so still the same, but times du dx, which is the derivative of u. Or we can also think of it as e to the u times u prime. If I want to say this in words, the derivative of e to the u is e to whatever u is times the derivative of u. So the derivative of the exponent. So let's put this into practice. On part A, I can see that y equals e, and then there's an exponent that's more than just x. So we'll work on some derivatives here. The derivative with respect to x of e to the 2x, so now I'm going to think of this whole thing as being the exponent. So remember the derivative rule, I guess to u, of e to the u is, just copy it down, times the derivative of the exponent. So when I go to work on example A, it's e to this exact same exponent. And then I'm going to multiply it by the derivative of the exponent, 6x squared minus 3. Make sure you put that in parentheses because we want the whole thing being multiplied by e to that power. Let's try part B. Part B says y equals e to the 1 over x. It might also be useful to think of it as e to the x to the negative 1, because 1 over x is the same as x to the negative 1. So if I take the derivative here, I'm just going to copy down e to the x to the negative 1, and then I will multiply it by the derivative of x to the negative 1, which is negative 1x to the negative 2. Then on C, same deal. dy dx, just copy the entire problem down, but then we multiply by the derivative of the exponent. So negative 16x to the third. Now again, the reason I have to use this version is because the exponent is a little more complicated than just x. Oops, it's supposed to be a highlighter. Each of those exponents are not just x. They are something else. So that's why we'll have to use the chain rule. Next up, we have derivatives of more exponential expressions, but this time the bases are not e. The bases, the number that has the exponent, are just some other number. So we are going to pay close attention to the chain rule version. I'm going to zoom in on the particular derivative rule, which says if I am taking the derivative of a base to an exponent, so a is going to be my base, u is going to be the exponent, then I will get the natural log of the base times that same a to the u expression times the derivative of the exponent. So if I want to write that down in words, natural log of the base, then you're going to multiply it by the expression, so copy down original. And then that will be multiplied by the derivative of the exponent. And we'll do this anytime I have an exponential expression. So I've got an x in the exponent, but the base is not an e. The base is some other number. So if we look at a, and I want to keep that rule in mind up there. Okay. I'm taking the derivative of 5 times 5 to the 8x to the 6th power. So my derivative, dy dx, I'm going to start off by saying natural log of the base, 5, and then I'm going to multiply that by this original expression, 5, 8x to the 6th, and then that is going to get multiplied by the derivative of the exponent. So derivative of 8x to the 6th is 48x to the 5th power. Let's do one more of those and then we'll move on. Okay, so for part B, dy dx, I'll start off natural log of the base here, which is 6. Then you're going to multiply it by the entire expression, 6, negative 6x to the 4th minus 2x cubed. Then multiply by the derivative of the exponent. So negative 24x cubed minus 6x squared. All right, derivatives of natural log functions. So anytime you have a function where there's a natural log or ln of something, we're going to need to use this rule. And more often than not, we've got to stick with the chain rule version, which says that the derivative of the natural log of anything is 1 over that thing times the derivative of the thing. In other words, the derivative of natural log of u is the derivative of u divided by u itself, as long as u is not 0, or as u is greater than 0. So, cut out my rule there. So on part A, natural log of 2x, if I go to find the derivative, the u part is the 2x right here. So the derivative of 2x is just 2. And then the u is 2x. And then that does simplify to 1 over x. For part B, dy dx, again, the u part that I'm looking at is x squared plus 1. So if I do u prime over u, which is the rule for the derivative of a natural log function, the derivative of x squared plus 1 is 2x, and then over x squared plus 1. And then for part C, dy dx, derivative of this part, negative 40 x to the 4th plus 20x cubed, and then just copy it down in the denominator, negative 8x to the 5th plus 5x to the 4th. And finally, derivatives for not just natural logs, but just logs. So if you have a function that is a log of something, and you have to take the derivative of it. We're going to stick with the chain rule version again. The formula is right here. Notice where a is. Notice where u is. So 1 over natural log of the a times u times the derivative of u. So I'll apply that formula here. Dy dx equals 1 on top, natural log. Now the formula says a, and a is the base. So in part A, my base is 3. So natural log of 3. Then I'm going to multiply that by u. So my u is this part right here. Negative 3x to the 4th minus 3x cubed. Need to extend my fraction bar. Then I need to multiply it by the derivative of the part that is you're taking the log of. So now I need to multiply that whole thing by the derivative of negative 3x to the 4th minus 3x cubed, which would be negative 12x cubed minus 9x squared. Now if I want to, I can just multiply that, treat it as over 1, multiply straight across, negative 12x cubed minus 9x squared over natural log of 3 times negative 3x to the 4th minus 3x cubed. All right, and that is how you'll take derivatives of log functions, derivatives of natural log functions, so anytime you have natural log of something, derivatives of anything with a base, so like 3 to an x power or 5 to an x plus 2 power, and then derivatives of your e functions. If you have any questions, let me know. Have a wonderful day.